Many chemical engineering problems are about trying to figure out how much energy you're going to get from burning a particular fuel. By burning, we mean combusting. And so combustion is just the reaction of that fuel with oxygen to create some sort of reaction products plus heat. And then that heat, again, is used to drive some other process. And so for most of our work, we're going to consider the combustion reaction involving a fuel that's a hydrocarbon. So it's a carbon or a compound that contains two chemical elements, hydrogen and carbon. There can be others involved as well. We can look at alcohols that have oxygen in them as well. But our primary focus will be on hydrocarbons. And so if we look at the history of kind of energy in the modern world, in the 19th century, primarily the fuel source used to create energy was coal. And so approximately you have about a 1-to-1 hydrogen to carbon ratio. In the 20th century, there's generally speaking a shift to oil, and so that improved that hydrogen to carbon ratio about 2-to-1. And then in the 21st century, you can say fuel cells are one option, solar and wind technologies are others, where we're trying to shift that, in all cases we're trying to shift that hydrogen to carbon ratio because that improves the efficiency of whatever process you have and has the byproduct of not releasing carbon into the atmosphere. So for most of our combustion events, we know the fuel, we know what the reaction products are going to be. What we don't know is how many of everything are involved. And so that's where stoichiometry comes into play. So hopefully this will be a review of our experience from chemistry. But if we take a look, for example, at the formation of water, we have a stoichiometric equation here that is a combustion reaction. So we are reacting hydrogen gas with oxygen to form water. And so to balance an equation like this, we have to have the same number of atoms of each element on both sides of the reaction. So I've kind of kick-started us here a little bit. We've got 2 moles of hydrogen gas. So that means I have a total of 4 oxygen or hydrogen atoms on that left side of the equation. And on the right-hand side, I've got B times H2. So I've got B times 2, or 2B, number of hydrogen atoms on the right-hand side of the equation. So I can balance my equation that way. In terms of oxygen, on this side, I've got A moles of oxygen gas. So therefore, I've got 2A on the left-hand side, and that's going to be equal to just B times 1, since that's a 1 there. So B on the other side. And so I can solve this system of equations. Here we can pretty easily see that B is going to equal 2. And then I can substitute that into the second equation, so that tells me that A is going to equal 1. And so then the resulting stoichiometric equation that I have here for the formation of water is 2 moles of hydrogen gas reacting with 1 mole of oxygen gas. It's going to be equal to 2 moles of water. In the next example, we're looking at the combustion of diethyl ether, which, as you can see here, has oxygen in it, so it's an alcohol rather than a hydrocarbon. And we've got a little bit more going on. That combustion is going to produce not just water, but it's going to produce carbon dioxide and water. So because we've got 3 different elements we have present in our reaction, we're going to need 3 separate equations in order to figure out what our stoichiometric coefficients are going to be. So we can first roll through carbon. On the left-hand side, we just have the 4 carbon atoms. On the right-hand side, we see right here that we've got B moles of carbon dioxide, so that's going to be equal to just B, so that's easy enough. For hydrogen, we can see that we've got 10 hydrogen atoms on that left-hand side. On the other side, hydrogen is only present in the water, so C times 2, so that's going to be 2C. And then for oxygen, we have on the left-hand side the 1 from the diethyl ether, plus we've got the oxygen that we're combusting in, so 2A equals, and then on the other side, again, we've got oxygen present in both compounds, so we're going to have 2 times B from the carbon dioxide, and then plus just C from the water. Now, fortunately, we've got one of our coefficients already solved for, and the second one we can solve pretty easily by dividing both sides by 2, so we get C equals 5. And then if we substitute both of those values into this bottom equation, we're going to get 1 plus 2a equals 2 times b, so 2 times 4 is 8, plus 5 is 13. And so if we solve for a, we're going to get a equals 6. So now our balanced equation, we can write it down as the diethyl ether plus, and then a is 6, so 6 moles of oxygen gas is going to produce, B was 4, so 4 moles of carbon dioxide plus, and then C was 5 moles of water. Now in this equation, we had as many equations as we had variables. There are some circumstances, as we're going to see, where we end up with more variables than equations, which means we would have an infinite number of solutions. So what we do then is we attempt to balance one of the atoms and then use that to fill the rest, and then we just want to end up with the smallest value of those coefficients ratio as possible. In this next example, I've got to figure out the coefficients in front of all 4 of my compounds in my reaction: the methane, the oxygen, the carbon dioxide, and the water. And so I'm going to need to set up a system of equations to find those coefficients. But in this case, we only have 3 elements, so I'm only going to be able to create 3 equations. So we'll start with the carbon. And so on the left-hand side, I see I have just A for the carbon, and then on the other side, I have C for the carbon. So that's my first equation. My second equation, I can go through the hydrogen, and so I've got A times 4 from the methane here, so 4A, and then on the other side of the equation, I've got hydrogen present in the water, so that's going to be 2 times D. And then finally, I need to do the same thing for the oxygen. So on the left-hand side, I have the oxygen gas, so that's going to give me 2B. Then on the right-hand side, I have oxygen present in both elements, so I have 2 times C, and then plus D. So the challenge here is I have 3 equations, but 4 variables. So what we can do is we can establish a value for one of these variables and then use that to solve for all the others. And then if we have any decimal values, fractional values, when we go through and use that, we adjust to make sure that we have integer values for all of our coefficients. So we start off, and if we just assume that A equals 1, then that would lead to C being 1, since A equals C. I can then plug into my hydrogen equation to figure out what D is. So if I've got 4A equal to 2D, I've got 4 times 1 is going to be 4, so that means D is going to equal 2. And then I can plug into the oxygen equation. I've got 2B equals 2 times C, which we've established is going to be 1, so 2 plus D, which we solved for, which is 2. So we can see that we're going to end up with 2B equals 4, or B equals 2. And so since these are all integer values and they are the smallest possible ratio, I've got the coefficients of my stoichiometric equation, so I can just substitute 1 in place of A, 2 in place of B, in place of C I'm going to put 1, and then for D I've got 2. So 1 methane plus the 2 moles of oxygen yields 1 carbon dioxide plus 2 moles of water. For our last example, we're looking at the combustion of butane. So we're going to have the same circumstance where we're going to have 3 elements leading to 3 equations, but we've got 4 variables since we have 4 coefficients we have to solve for. So in the case of carbon, we've got 4A on the left is equal to C on the right. For the hydrogen, we've got 10A on the left is equal to 2D on the right. And then for the oxygen, on the left we've got 2B, and on the right, again, oxygen is present in both compounds, so we've got 2C plus D. So once more, we've got to pick one of our variables and establish a value for it, and then use that to solve the rest. So I'm again going to go with A is 1, see how that works out for us. So I've got A is 1, that makes C equal to 4, since 4 times 1 is going to be 4, so that gives me C. If I plug in 1 down here into my hydrogen equation, I'm going to get 10 equals 2 times D, so D is going to equal 5. And then I can plug into my last equation to figure out what B is. So I've got 2B equals 2 times C, so 2 times 4 is going to give me 8, plus D is 5. So this time I get 2B equals 13, or if I divide both sides by 2, I get 13 halves. So the problem I have here, make that look like a 2, there we go. So the problem I have here is I need integer coefficients for a final result. And so since I ended up with a fractional value, I need to multiply everything here by 2 in order to clear that fraction, by whatever the common denominator is of any of the fractions that I end up with. So we're going to end up with A is 2, B is 13, C is 8, and then D will be 10. And so then I can just substitute those into my equation here. So I'm going to end up with 2 of the butane plus B is 13, so 13 moles of oxygen is going to yield 8 moles of carbon dioxide, and then finally 10 moles of water.